All right, well, it's 1 o'clock and it looks like it's me and you. So we're going to go ahead and get started. Feel free to use the talk feature since there's just the two of us. And we'll kind of go from there. Interrupt me at any point in time. We'll go the speed you want to go. And it'll be a fabulous, fabulous day. I did remember to hit record, so it is a good day. I apologize. I'm a little scratchy today. I'm recovering from something. So if you don't understand or I need to be louder, just let me know. So. All right, so this week we're covering two sections, 14 and 15. They are very much related, so that's nice. Then you have a quiz and a discussion board, so really kind of a light week when it comes to the work. You should be working on project 2, hopefully. Project 1, right, was due a while ago. My goal is to have those graded by next Sunday. I'm out of town Thursday through Sunday, and then next week I'm out of town Wednesday through Friday. Ooh, we got to talk about that too. Crap. I just thought about that. Okay, we got to talk about that later. Don't let me forget. But I do plan on having those graded by the end of next week so that you can make sure if you need to tweak project 2 at all, there's time to do that before it's due. And then exam 2 is coming up at the end of the month. So that's due the 28th at noon. So you might want to think about scheduling that as well. So, all right. So Lillian, do you have any questions before we get started?
Nope.
All right. Oh, here we go. There we go. Okay, so section 14, the normal distribution. When we talk about the normal distribution, we talk, we're talking about, basically, that's not very straight. We have a bell-shaped curve. And a normal distribution means that the data all falls underneath here. The data, we call this being normally distributed when it falls in this lovely pattern. Now, to be normally distributed, it's got to fall in this pattern, which means this middle piece is the mean, the median, and the mode. So when we talked about being skewed back in section 8, we talked about how the mean and the median were related. And now with the normal distribution, we are symmetric. 50% of the data is on each side, and the mean, median, and mode all fall directly in the middle. So the nice thing about this, with having 50% on each side, you know that 100% of your data falls under this curve. So just kind of in general, if I have a different curve, we're leading up to a question just to prepare you. If I draw a line here and say 70% of my data falls to the left of the blue line, well, what does that mean? How much falls on the right side of the blue line?
30.
Exactly. So if you can keep that in mind, if the whole thing is 100%, so if I have a vertical line anywhere, if I know how much is on one side, I automatically can figure out mathematically how much is on the other side, because together they have to add up to 100%. So that is kind of an important piece. Okay. I don't remember what my next page is. I want to look at that. Okay, before I want to erase, I'm going to stay on this page. Now, with the normal distribution, we talked about the mean. The mean is in the middle. The other piece to the normal distribution is that we deal with the standard deviation. Do you know what standard deviation is?
No.
Okay, standard deviation simply means how far is, standard deviation talks about the spread of data. So if you have two different graphs here, you can see they are very different in how they look. They're both, if they were drawn well, normally distributed, but I would call this one high and tight. So you can see how most of the data is very close, right? The mean is in the middle. Most of the data is really close to the mean. So this would have a small standard deviation because my data is not very spread out. Your standard deviation talks about how spread your data is. Small standard deviation means it's very, very compact, huddles around the mean. Whereas on this right side, you can see that it's short and fat. It's a lot more spread out. So this one would have a larger standard deviation, which is known by this sigma symbol. So if you just have a graphic, if it's tall and skinny, small standard deviation, short and fat, large standard deviation. And when I say small and large, how is that quantified? Well, it depends on your data. So that's who knows. It could depend on a lot of different things. But you can expect, if you had these two graphs, that this standard deviation would be larger than the one on the left. And we're not going to calculate standard deviation by hand, but you may. Yeah, I think you do have to do it in Excel. So Excel will do the formula for you. The Excel or the formula for standard deviation is a beast. It's pretty long. Um, the math in itself is not hard. You subtract, you add, you square, you divide, but it's a lot of process, and there's just no reason for all that business. So we need to talk about standard deviation because that is part of dealing with the normal distribution. So we're going to play now. Section 14 deals with the empirical rule. And I like the empirical rule. I think it's fun. I think it's pretty easy to understand for the most part. It's not all that practical when it comes to mathematics, and we'll see why here in a bit, that there are limitations. So I don't remember what page in your packet. I want to look it up real quick. Page 122 is kind of the intro page for the empirical rule. You don't have to look at it. I was just kind of giving you a reference. But I like to really go through why or how you get the numbers that you get when it comes to that page. So I think it's great that they give you this page and they give you all of these numbers, but I'm a person who wants to understand. If I don't know why things are the way they are, it doesn't make any sense to me. So I do have a short video. It's 2.5 minutes. It's called The Empirical Rule. I'm going to do the same thing right now, what I do in that video. So if this one goes too fast or it doesn't make sense or you want it to be maybe a little clearer, you might want to look at that video later. So, man, my lines are struggling today. Here's the mean in the middle. And I don't know about you, but I struggle very much in the abstract. So just saying that's the mean, well, what is the mean? If I don't have numbers, I have a little bit harder time. So we're going to pretend for our example that the mean is 70, excuse me, and the standard deviation is 5. That will allow us to actually deal with concrete numbers while we're looking at this example. So we know the mean falls directly in the middle, and I know that my mean is 70. So there's that value. Okay, so far so good? Great. When dealing with the empirical rule, you always want to start with the mean. You always want to be, and that's always in the middle. Now, the empirical rule is also sometimes called the 68, 95, 99.7 rule. And the reason I bring that up now is because we are going to talk about what these mean. So 68%, that means 68% of our data will fall one standard deviation from the mean. And that's one standard deviation in both ways. So if I go to the right, I'm going to add a standard deviation. So the mean plus, so if the mean is 70 and the standard deviation is 5, well, 70 plus 5, that value would be 75. And if I go the other direction, I'm subtracting, so that's the mean minus the standard deviation. So 70 minus 5 is 65. So we would say from 65 to 75 is 68% of my data. So maybe these are test scores. So we could say 68% of students scored between a 65 and a 75 on the exam. That would be an example of using that. Okay, so 68% is one standard deviation away. Well, 95 is the second number. So that means that 2 standard deviations away would be 95% of our data. Oh, wait, back up. Okay, from green to green, if that's 68% and this red cuts it in half, 68 divided by 2 is 34. So that's why if you look at page 122 in your packet, there's a 34% in each one of those spots. Because total is 68%, it's got to be symmetric, right? The same on each side. Okay. Let me know if that doesn't make sense. Okay, so now into orange. Now we are 2 standard deviations away. So mean plus 2 standard deviations. So again, I'm another standard deviation away. I add 5 again. When I go to the left, I'm subtracting another standard deviation. So that puts me at 60. So now, from orange to orange, that is 95% of our data. But when we're thinking about these places, we don't just take 95 and we divide by 2 because the green is already taken care of. So I would say, well, we have 95 from orange to orange, but The 68% from the green is taken out. So how much is left to be represented in those two orange spots?
So it'd be 95% minus 68%.
Yep, that's our first step.
27.
Okay, so there's 27% is left, and that fits in these two spots. But we know that needs to be divided equally because the normal distribution is split, it's symmetric. So I have to divide that by 2. So how much goes in each spot?
13.5.
13.5. All right, so this is how we're getting these numbers, basically. Okay, so 95% is 2 standard deviations away. And then we go to 99.7, it's the third number. So we are now 3 standard deviations away. So mean plus 3 sigma on the right would give me 85. Mean minus 3 sigma on this side would give me 55. So from pink to pink is 99.7% of our data. But same concept. If we had 99.7% of our data, and we already know that 95% of that is from orange to orange, how much is left in this pink spot? Oops, wrong color there. So we subtract
4.7.
4.7. And again, they're symmetric, so we divide that by 2.
2.35.
Perfect. Okay. So that's the rule. That kind of just tells us these pieces. But then if you think about it, we know this entire curve is 100%. And we only have 99.7%. So if I say the whole curve is 100%, and I take out the 99.7 that goes pink to pink, we have 0.3% left that needs to be split between what I call the two tails, right? This tail and this tail. So that gives us 0.15%. So that's how they come up with these numbers in the empirical rule. And the nice thing about the empirical rule is that these numbers never change. That's a nice thing. And then we can use them to find probabilities. So in this particular example, if I said, what percentage of students scored between a 75 and an 80? Well, here's 75, here's 80. So between them would be 13.5%. Or if I said, what percent of students scored less than a 65? Well, here's 65, less than would be everything to the left. So I would add those 3 percentages together, and I have 16%. So you can use this in different ways to calculate probabilities in a problem. Okay. Any questions on how I came up with those numbers or anything?
I mean, I get it. I just don't understand what it's going to be used for in the homework, I guess.
Well, that's the next problem.
Okay.
Yeah, I like to understand where the numbers come from. To me, I don't like to just look at a piece of paper and say, oh, those numbers are there. Okay, I'll use them. For me, it's helpful to know why. Where did they come from? So, the purpose of this slide was that if we're going to use this 68, 95, 99.7 rule, how does that transition into these problems that we're going to do our homework? So, okay. So yeah, let's jump into what is this going to actually look like. All right, so we have a problem. The average miles per gallon in luxury cars is 29 with a standard deviation of 3. We're going to draw a normal distribution curve labeling through 3 standard deviations away from the mean. Then we're going to answer 4 questions. What is the probability a car gets less than 23 miles per gallon? What is the probability a car gets more than 23 miles per gallon? What is the probability a car gets between 20 and 32 miles per gallon? And how likely is it a car gets more than 38 miles per gallon? So the purpose of that curve with all the numbers is that using the empirical rule, we can answer these questions. Without the empirical, there's another way to do it. That's section 15. But for some cases, the empirical rule can be used. Okay, so the first thing we're going to do is change the screen. Maybe. There we go. We're going to draw the normal distribution curve. So, I might change colors. Got the curve. I swear my curves are better in person than on a screen. All right, we always start with the middle. What number's going to go in the middle?
29, was it?
Yep, good. Good memory. So we know the mean is 29, and the standard deviation is 3. All right, so going to the right, I'm just going to get some more. They want us to go 3 standard deviations to the right, 3 standard deviations to the left. So see if you can put those numbers in there. I'll just give you a minute or so. You good?
Yep.
Okay. So when we move to the right, you added 3. Okay. Moving to the left, you subtracted 3. Right?
Yep.
I should say correct. Okay. So you sketch this out. I put in the numbers, right? And again, remember the gray percentages, those are constant for every time you use the empirical rule. You don't have to have them memorized. It's not on your formula sheet, but you don't have to use the empirical rule on the exam. Anything that it asks for probability, you can use z-scores, which is section 15. We'll get to that in just a moment. But you can use the empirical rule if you want. You just have to have them in your own head. That's up to you. Okay, so anyway, so we did this. Now that we have a visual, now we can answer some questions. So I'm going to leave it on this screen as I recall the questions. That way I can show things on here. So question B was, what is the probability a car gets less than 23 miles per gallon? Okay, so if you have this taken care of, you locate 23. Well, 23 is right here. If I'm talking about less than 23, where is that at?
Everything to the left, 23.
Everything to the left. Okay, so we add those two together, 0.15 and 2.35.
2.5.
Exactly. So to the left, less than 23 miles per gallon, you have a 2.5% chance of being, so that's the answer to B. C said, what is the probability a car gets more than 23? Now, remember from a couple slides ago, and I'm just going to re-diagram it up here. We have a vertical line, and we said on the left is 2.5%. So if I want, that's less than. If I want more than, that's everything on the other side. What's a quick way of figuring that out?
100 minus 2.5.
Exactly. So 100 minus 2.5, and that gives us more than 23 would be 97.5%. Now, you could go through and add all of these percentages up, but that is a whole lot more work than just subtracting from 100. Okay. So that was C. D said between 20 and 32. So now we have kind of stipulations. I need a color. So here's 20. Here's 32. We want between them. So what are you going to do?
Add everything between the pink lines.
Exactly. So if we add those 4 together,
83.85.
yes. So I was looking at the wrong number. I'm like, that's not right. Yes, so 83.85%. So if your goal is to get a car that has between 20 and 32 miles per gallon, that's the percentage that you're looking for. Or that's the probability of it actually happening. And then letter E was the wording changed ever so slightly. What is the likelihood, or how likely is it, that a car gets more than 38 miles per gallon? Well, here's 38. Which way are we looking if we're talking about more than 38?
Right.
To the right. So we look to the right, and your probability is 0.15%. So if the question is how likely, you would say, well, it's not very likely. There's only a 0.15% chance. But you still want to use that 0.15% because that quantifies your answer. Right? You can't just say, well, it's not very likely. Well, does that mean 10%? 20%? No, 0.15%. It's super not likely. So even if it doesn't straight up ask for the probability, you still want to use that probability to quantify your answer. Okay. Okay. All right. Any other questions on that? So that's an example of how you would use the empirical rule. Does that make sense?
Yeah.
Okay. Yeah. It definitely helps when you actually put a little application to it. So now there are limitations to the empirical rule. So if you'll notice, there are only 7 numbers present. So we can find probability less than, greater than, between these 7 numbers. And that's it. So if you said, well, I want a car that gets greater than 30 miles per gallon, well, 30 is about right here, but we don't know how much, how much does that cut off? I don't know. So it's only good for 7 numbers. That's a very big limitation. And that's why the empirical rule is not used all that often, because of that huge limitation. But it's great for general estimates using probability, and yeah, which is why it's important. And I think it's kind of fun. Once you understand and you get going with it, the problems are not all that difficult once you get going with it. So it's not too bad. But that's going to lead us into section 15, because section 15 says, okay, we want these probabilities. We want to play with this material, but we want to play with all of these values in between. We want to play with 30 and a half and 35 and a half and 32.23. We can play with all of those values using z-scores. And so that, my friend, is where we're going to go next. Okay. So that was section 14, empirical rule. So z-scores are a way to standardize data. And I always tell the story to my face-to-face classes, so I'm going to share it with you as well. So when I did my dissertation, this is a real-life application of z-scores. I was working on my dissertation, and I had 2 sets of data. Oops, I thought I had a pen. I had 2 sets of data. I had AccuPlacer scores, because I was dealing with placement testing, and I had Compass scores. Compass is the test that we use before AccuPlacer. And so I had a bunch of numbers. Well, it came to be that, let's pretend the average for the AccuPlacer was a 40. I'm making numbers up. And the average for the Compass was 62. So basically, if you used a score of 62, now you would score a 40. So I had all of these numbers over here, all of these numbers over here, but they didn't gel, because all the Compass numbers were higher. If you scored a 62 in AccuPlacer, you're way above the mean, but a 62 in Compass, you were the mean. So what I did, I took all these numbers, I found the mean and the standard deviation of each one, and I turned them all into z-scores. Because for the mean, the z-score for a mean is 0. So if I did this for both sides, whether you had a 40 on an AccuPlacer or a 62 on Compass, your z-score turned out to be 0. And when I did this then with all of the numbers, now I have a common data set where they're all speaking the same language. So instead of these numbers being all jacked up and different, they're all z-scores. Standardized, common language, I can put them in one data set, now I can use them. So if you're trying to make comparisons, it's hard to compare 2 data sets. People talk about comparing apples to oranges, right? That's what I had. I had apples and oranges. So what I did is I did magic, and I turned them all into grapefruit, and then I could use them together. So that's what z-scores do. They turn things into grapefruit. I don't know if you can sell that process, but it kind of works. So here's the deal. What is a z-score? A z-score is the number of standard deviations from the mean. That's a basic definition of a z-score. So when I'm talking about, we've got our curve here. I know that my mean is in the middle. Well, if we're talking about z-scores, the z-score for a mean is 0, meaning anything to the right of 0 is going to be positive. So all the positive z-scores go on the right, and everything to the left is negative. All right, so you have positive z-scores on the right, negative z-scores on the bottom. So if I would have a z-score of 2.3, that means that this value, whatever I use to find it, that value is 2.3 standard deviations above the mean. That's what the z-score stands for. Okay. And again, I think as we do some of these problems, it makes more sense when we get to some applications. But that's by definition, a z-score is the number of standard deviations from the mean. If it's positive, you're above the mean. If it's negative, it's below the mean. So a negative 1.4 would be negative 1.4 standard deviations below the mean. All right. General definition. Okay. Formula. Formula for a z-score is x minus mu over sigma. I throw that at you first because that's what you'll see on your formula sheet. So on that page 246, so the back of the conversion sheet, underneath that big table, which we're going to use here in just a moment, you see z equals x minus mu over sigma. There's your z-score formula. But if you don't know what those values mean, right, it's worthless. So a z is the z-score. X stands for the value. The mu stands for the mean. And sigma is your standard deviation. So the nice thing is, a lot of problems you'll read and they'll say the mean is whatever and the standard deviation is. So they're going to identify the mean and the standard deviation for you. Then whatever value you have left, there's your value. There's the value. There's x. But until you really get comfortable with this formula, you might find it useful to actually say this out loud. Value minus the mean divided by the standard deviation. And it also helps if I tell you the mean is 70 and your value is 65. Well, if your value is less than the mean, what do you know about your z-score?
It's negative.
It's going to be negative, exactly. And don't lose that just general knowledge, because it's very easy to flip-flop the value in the mean, but the flip-flopping will change it from positive to a negative or vice versa. So make sure you're keeping in mind when you're looking at your data of, hey, I should have a negative z-score based on my data. So when you do the math, make sure it actually does come out negative. That's super important. Okay, one other thing before we jump into an actual problem. Oh, I should look at my next slide because my next slide is the formula, but I just did that. That's okay. Okay, I want to talk about the table. So do you have your yellow sheet with you?
Oh, which one? The
formula.
customer units.
Yes, you do?
Yeah.
Okay. Great. So I want to make sure that we know how to use that table because that's, oh my gosh, I finally drew a straight line. It only took me 29 minutes. All right. So we've got ourselves the normal distribution curve. And so we did some math, which we will actually do here in a minute. And we come up with a z-score of 0.4. Okay. The purpose of a z-score, right, it tells us how many standard deviations we are from the mean, but it also allows us to find probability. So if we want to find the probability that somebody scored less than blah, 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 whatever, their z-score is 0.4. If you look at the table, you'll notice that you have four columns. Within each column, you have a z-score and a corresponding probability. So if we find 0.4, which is in the third column, you'll see that the probability attached to that is 0.6554. Do you see what I'm seeing?
Yes.
Okay. The thing to remember, and I wrote it on here to kind of help put this in your head, the table always gives you area to the left. Always. So when you look at the table, and this is why I highly recommend you sketch, curves, and you put your z-score on there with a vertical line, because then when you put the data in from your table, it goes into the left of that vertical line. So now I can say, okay, if I wanted to know the area on the right, if I want to know this over here, how do I get there? We talked about it a little bit earlier in a different way, but same concept.
Would you just do 1 minus 0.6554?
Absolutely, absolutely. With the empirical rule, we were dealing with all percents, right? Well, now we're dealing with decimals. So you absolutely did it 100% correct, that the whole thing is 100%, which is 1. And if we take that 1 and we subtract the stuff on the right, which is 0.666554, the leftovers, which is 0.3446, is the area on the right. So you just have to remember, table gives me area to the left, and if I want the right, I just have to subtract. So the same concept that we did in section 4. Okay. So far, so good?
Yep.
Okay. Let's see here. Okay, so let's do a problem here. Average calories burned at the gym is 460 with a standard deviation of 35. What is the z-score of somebody who burnt 510 calories? Do you remember the formula?
Z equals value minus mean over standard deviation.
Perfect. Okay, try it.
Okay, I probably don't have this right, but would it be 10 over 7 after reducing?
Yes. So change it to a decimal.
1.428. Or how far do you want me to
Yeah,
go?
that's good. That's perfect. That's totally great. Good job. Very good. Now, one thing, I'm just going to say this for the good of the group that may be watching this later. If you type this all into your calculator at one time instead of, we went fraction to fraction, by putting your numerator in parentheses and doing 510 minus 460 in parentheses, you can actually do it all at one time. 510 minus 460 and parentheses, divide by 35, and it'll get you to your answer. But if you don't use those parentheses, it will jack up your answer. Okay, now 1.428 is a fabulous, fabulous z-score. And if we were in a statistics straight stats class, we would have a z-score table that was multiple pages, and we could look that number up. However, we are in a quantitative reasoning class. We're kind of, we shortened our table quite a bit to just half a page. So if you look at your table, this is just for future problems here, what z-score is closest to 1.428?
1.4.
1.4, exactly. So if we were using this z-score, we would use a z-score of 1.4. So you're just going to whatever is closest. Yeah, good. Okay, now we're going to use that for the next part of this problem. So luckily you have that written down. All right, so part B. What is the probability of somebody burning less than 510 calories? Okay, so we just found, oh my gosh, that curve is horrible. I have to start over. This is horrible. Okay, so we just found that the value of 510 has a z-score component of 1.4. And that's always your first step with these. If you have a mean, a standard deviation, and a value, and you want probability, you find your z-score, because that standardizes the data. I'm a big visual learner, so I'm a big fan of saying, okay, 1.4 is to the right of the mean. I know that the mean is in the middle. So 1.4 is going to be somewhere over here. Now, if you're going to burn less than 510 calories, which side of this green vertical line do I want to be on, the left or the right?
The left.
Perfect. The left. Because remember, this z-score of 1.4 represents 510 calories. This is kind of like a number line, right? This horizontal line is a number line. So the numbers are going to get smaller as we go here. Remember that the mean is 460, right? So that's keeping that in mind. Okay, so we want less because that's what the question is asking. We want area to the left. How do I find the value of that area to the left? So area to the left, probability mean the same thing. If we look at our table, find a z-score of 1.4.
Right, like find the probability for 1.4.
Yeah.
0.9192.
There you go. So the answer to that is 0.9192. So basically there's a 91.92% chance that someone will burn less than 510 calories at the gym. That's what that means based off of this data. Does that make sense? Yes, no?
Yeah.
Okay. So z-scores allow us to really locate on our normal distribution where our value lies. And then using the table, that z-score allows us to find the probability of less than or greater than that value. So using a 5, we found from the previous problem that 510 corresponded to a z-score of 1.4. From our table, we know that 1.4 corresponds to an area of 0.9192. The area is equal to the probability. Those two things are the same. Now, that leads us then to the next question, which is what is the probability of somebody burning more? Oop, crappers. Here we go. I hit the wrong button. There we go. Burning more than 510 calories. Well, which side are we looking at if we want more than 510 calories?
To the right.
The right. So now we want this side. And how do I find the gray side?
Take 1 minus 0.9192.
Exactly.
Zero 0.0808.
0808. That's an ugly looking 8, but there it is. Yeah. So if you're like, man, I really want to burn more than 510 calories at the gym, you're like, well, you've got an 8.08% chance of that happening. Probability. Based off this data set. Okay. All right. I'm going to have you try one. From the beginning. You're still going to use the same 460 calories as your mean, 35 is your standard deviation. But now you're going to answer the question, what is the probability of somebody burning less than 400 calories? So I want you to try on that. Let me know when you're ready or you're stuck.
Okay, can I guess?
Sure.
Is it 0.0446?
It is. Very good. So for the folks at home who are watching, what'd you do first?
I took 400 minus 460 over 35 and got negative 1.7.
Excellent. So we started with the z-score, negative 1.7. So we know negative 1.7 is on this side. Which way are you looking, left or right?
To the left.
Left. So we want this side. Go to the table, find negative 1.7, and that's where the 0.0446 came from. Very good. Right? See, not bad once you understand what you're doing. Okay, good, good. All right. This one's a little bit different. Same gym problem, same mean, same standard deviation. But now we want the probability someone burns between 440 and 500. So now we're not just going to the left or just to the right. So start with finding z-scores for both of them, if you would be so kind. And you're going to have to round for both of them.
We round to 0.55 or 0.6.
It's really up to you. It's whatever you think is closest. I mean, you end up with negative 0.57. So if you go with what's closest, you would end up with negative 0.55. If you went to negative 0.6, there's nothing wrong with that. It's one of those, if this was on the exam, you would want to make sure that you had that on your sheet, your scrap paper, so that when you turn in your scrap paper, if your answer doesn't match my answer, I can look at your scrap paper and say, oh, she went to 0.6, I went to 0.55. Everything else is perfect. She gets full credit. She knew what she was doing. She rounded the other way. There's nothing wrong with that. You just want to make sure you document that. And actually, I think on the test, I don't think any of them are that close, if that makes sense. I think they're more like it'll come out to be 0.55, so it's right on. Yeah. What'd you get for the other one?
$1.1.
All right. So I have my z-scores of negative 0.55 and a z-score of 1.1. Now, just for fun, those correspond to values of 440, and this corresponds to a value of 500. Okay. So our goal in this problem is to find the probability between. So we want to find this shaded area, which causes a little bit of confusion because we have, all these area on the sides. So do you have any idea how we would find just that area in between?
No.
Okay. So if we think about it, if I'm going to start with 1.1, if I go to the table, 1.1, it's going to give me all of this, right? Area to the left. So if you find 1.1 on your table, what is the area to the left of 1.1?
0.8643.
Great. So that blue line indicates 0.8643. Now let's do the same thing with negative 0.55, which gives me everything to the left of that.
0.2912.
Struggling with my decimal point. Okay. Now, what do you notice? Well, do you notice anything, I guess should be the better question.
I'm guessing you have to subtract them.
Fabulous. Why would you guess that?
Because I don't know. I'm just guessing.
Well, so it's a great guess. So if you subtract them, the pieces of the lines that are the same will disappear, right? These will disappear because when you subtract, those two pieces kind of go away. And you're just left with the blue piece that is between the two yellow lines. So if I take my 0.8643 and I subtract my 0.2912, I'm left with the shaded piece in the middle. Because we know that orange, 0.2912, only represents the tail. Well, the blue represents the tail and the middle piece, and we don't want the tail. So if I take the tail plus middle piece, subtract the tail, I'm just left with the middle piece in terms of using words, I guess. That was a lot of words. And we end up with
0.5731.
very good, 0.5731. So that's the area in the middle there. Okay. All right, and that's section 15 in a nutshell. So the empirical rule and then standard deviation or z-scores. That's today. Now, I totally forgot until talking. Next Wednesday, I leave super early in the morning to go to Houston, and I don't know when I'm going to be available. So I know we did it 2 weeks ago. I think it was 2 weeks ago. Maybe it was last week. It was last week. Dear Lord. So can we rearrange this and do this session on Monday instead of Wednesday?
Yes.
Okay. I mean, you're here. So what time do you want to do? I think I have some. I have class in the morning on Monday. But that's about it. So what time is good for you?
I get home from work around 1:30. So anytime after 1:30.
Okay. So how about 2? Or do you want to do it later? 3?
2's fine.
Okay. So let's plan on next Monday at 2:00. It's going to have to be, you're going to have to re-register because it's a new session again. But I will get that fired up and get that posted in an announcement. If other people join us, great. If they don't, this worked out real well today, me and you. So we'll plan on the 16th at 2:00. And hopefully, as of right now, that's the last Wednesday I'm going to be traveling. So knock on some wood. And we should be good to go there. So awesome. Okay, so the 16th at 2. Do you have any other questions about anything?
I don't think so.
All right. So next week we will finish Unit 2, Sections 16, 17, and 18, and that means in 2 weeks then the session it'll be exam week. So that is crazy how quickly that flies. So if you haven't scheduled your exam yet, you might want to look into doing that pretty soon, so that you can get the day and time you want. And other than that, if you have any other questions, just shoot me an email and we'll go from there.
Okay, thank you.
Yep. Have a good day.
Oh.